Hey, so welcome back, and this is another daily code problem. So today it's called minimum number of vertices to reach all nodes, and it's yet again a medium level question, but it's a graph problem here. And so I actually read this wrong initially, so I'm going to try to make sure I explained it to you right. So make sure to read the description and read the example. Sometimes it's very easy to race right into the implementation, but I encourage you, don't do what I did today, and just take your time. It's a simple, it's a simple algorithm, but it's a simple question to understand what they're trying to ask you. So I didn't read it. I thought I initially just exactly looking at the question knew what they wanted, but I ended up just wasting like 10 minutes on writing the wrong algorithm. It was a different problem I was thinking of. But anyways, so basically, all that you want to do is find the minimum number of vertices, or I like to call them nodes, that will reach all the other nodes in the graph. And so in this case, what that really means is, okay, this node 0, it can reach not just 1 and 2, it can reach those, but you also want to consider that it can also reach 5. Through this relationship, through the second node. So it's not just what it's directly attached to, but effectively what it's able to touch through these relationships here. So it's not just like its direct children, but also their children's children and so forth. And so in this case, just using node 0 and node 3, you can reach all the other nodes, and that's because, well, you can reach 0 and 1 here, 3 can reach 4, 4 can also reach 2, and then they can naturally also reach 5, and that's all the nodes. I think this is a really good example of showing you what they're trying to hint you towards how to implement the algorithm, and we'll see that here. So if we start off with 2, it can reach 4, and it can reach 1 here, and then 3 here. Although you already reached 1, you have to use 3 because, well, nothing else can reach 3 except for itself. And so you use node 3 here. And same thing with 0 here. You have to use 0 because nothing else can reach 0. And so although other nodes have reached 1 already, and that's the only use for 0, you still have to use 0 in order to make use of it. And so what the pattern you might start seeing here is basically any of these nodes that I think of them as roots when they have no edge pointing into them, you need to include in your output. And so that's exactly what the algorithm is actually any node without an incoming edge, you have to include. And I think it wasn't until I really kind of looked at this example here that it clicked where, okay, there's a pattern here where whenever we don't have an incoming edge, we need to include it. And then as you begin thinking, you realize, okay, that's all I need actually. I don't need anything else except for nodes without an incoming edge. So yeah, fairly intuitive question, but looking at a question like, or an example like this is really helpful. So yeah, let's go ahead and implement it. So what we're given is kind of an adjacency list here through a two-dimensional array. So we're going to make use of that to find out, okay, which of these has an incoming edge pointing into it. And so we just say, okay, let's go through every source and destination. So this is the source node, and this is the destination node. This is the one that has like the incoming edge here in our edges array. And we're going to create an array called like has like incoming edge maybe, or has an edge, we'll call it. And initially this is going to be all set to false, and n is given to us, and that's the number of nodes in our graph. And it's false because, well, at the beginning we're seeing that none of them have an incoming edge, but all these destinations and these edges has an incoming edge. And so you can easily just say, okay, let's update this at this particular node for this destination to true as we iterate through here, and that's how we get which ones have and do not have an incoming edge. And then after that, it's just as simple as, okay, let's go through all of these nodes has in edge in our array here, but we want to enumerate it, and that's because we want to make sure we know which particular node that we're talking about. So this is just to keep track of, okay, does node 0 have an incoming edge? Does node 1 have an incoming edge? And so forth. Because this is just the true or false part, has incoming edge, the value that's stored there. So we need the index too. So we enumerate it. And then we just say, okay, if it does not have an incoming edge, so we just not the operation, then we want to include it in our output. So I like to call it response. So let's add to our response array this particular node I. And so let's create our array here. And then all that we want to do is just return at the end. Looks good. Let's try submitting. And success. So that's today's daily LeetCode problem. So for time and space complexity, well, it's O of n time complexity. And that's because, well, we just iterate through all these nodes in our edges, and same thing here, this edges array has the same number of nodes, so it's an O of n time complexity. And then for space complexity, it's same thing, it's O of n, where we're using this has in edges array to mark whether or not each particular node has an incoming edge. So yeah, hope it helped, and good luck with the rest of your algorithms. Thanks for watching.